Okay, guys, now for multiplication rule for independent events. Then we'll talk a little bit about what happens when we have to find the probability of at least one. So the multiplication rule for independent events says that if A and B are independent, then the probability of A and B both occurring would be the probability of A times the probability of B. So notice that this is significantly different than the general multiplication rule for probability, because that would have said that I have the probability of A times the probability of B after A occurred. But because in independent events, A does not affect B, A doesn't change what would happen for a second event. So it's not necessary to go through this, and that's why it's just times the second event. Okay, so let's look at a quick example here. All right. So, following the Space Shuttle Challenger disaster, this was, I think, in 1984, maybe later, I don't have it in front of me, in the Space Shuttle exploded during takeoff almost immediately. So it was determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. So under cold conditions, it was estimated that the probability that an individual O-ring joint would function properly was 0.977, assuming O-ring joints succeed or fail independently. What is the probability that all six would function properly? So they're telling you these are independent. So whatever's going to happen in the first joint would not affect the second joint or the third or the fourth or so on. So we have to find the probability of joint 1 being okay and joint 2 being okay. I'm saying okay, they're saying function properly. And joint 3 being okay, all the way to joint 6 being okay. So they're independent events, so I'm going to have the probability of joint 1 being okay times the probability of joint 2 being okay times the probability of joint 3 being okay. Okay, joint 4 being okay, joint 5 being okay, and finally joint 6 being okay. Now they're 0.977, so I'm going to do 0.977 times 977 times 977. Okay, but probably much easier would be 977 to the 6th power. It's an awful 6, which, give me a second, which would be about 0.87 or 87%. Okay, so now for finding the probability of at least one. So when we read this, it's going to make total sense to us, but it does get a little bit more complicated when we have to look at our examples. So the probability that at least one outcome happens is 1 minus the probability that no outcomes happen. So that kind of makes sense to us if we understand the idea of at least one of something happening. So let's take a look at an example where we'll see it's a little bit more involved than just this. Okay, so long example, but well, let's understand it. So many people who come to clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn the test results. Clinics now use rapid HIV tests that give a result while the client waits. In a clinic in Malawi, for example, use of rapid tests increased the percent of clients who learned their test results from 69% to 99.7%. So the trade-off for fast results is that rapid tests are less accurate than slower lab tests. So applied to people who have no HIV antibodies, one rapid test has a probability of 0.004 of producing a false positive, that is, of falsely indicating that the antibodies are present. Okay, so if a clinic tests 200 randomly selected people who are free of HIV antibodies, what is the chance that at least one false positive will occur? So I think it's important for us to realize that they're telling us one rapid test has a probability of 0.004 of producing a false positive. So what we're going to have to do, inevitably, is to find the probability of at least one positive, at least one positive. Okay, and to do that, I'm going to want to do 1 minus the probability of no negatives. I'm sorry, of no positives, rather. Oh, I just erased the whole thing. No big deal. Probability of at least one positive, okay, would be 1 minus the probability of no positives. Okay, so the probability of the outcome not occurring. So the first thing that I would have to do is actually find the probability of no positives then. So the probability of no positives would be 1 minus the probability of the false negative that they gave us, which was 0.004. Again, this was the probability of a false negative. Okay. And so that would give us 0.996. Okay. And now the probability of no positives, we're looking for with 200 randomly selected people, not just one, so this would be 1, so I have to do 966 times, you can either do it 200 times or you could give yourself an exponent of 200, and that's going to give you 0.4486. So we're still not done, because remember that this was ultimately what we had to do. And so now we'll do that now. So now I have to do 1 minus the probability of no positives. And the probability of no positives we now know is 0.4486. Remember, that's for one, that was for the 200. So I have 1 minus 0.4486, which is about 0.5514. Okay, so over 50% here would have at least one false positive. Maybe it wasn't as bad as I thought. Okay. Now you check your understanding. So I'm going to kind of do these with you, just for the sake of saving some time. Okay, so during World War II, the British found that the probability that a bomber is lost through enemy action on mission over occupied on a mission over occupied Europe was 0.05. Assuming that missions are independent, find the probability that a bomber returns safely from 20 missions. So this one's actually kind of similar to the last problem. So first off, the probability of return safely, I guess we have to, yeah, let's say return safely, okay, would be 1 minus the 0.05, which was that they were lost in enemy action. So that would give us the probability that they would return safely would be 0.95. Then, of course, we're looking for 20 missions. So we'll say the probability of them returning safely all 20 missions would, of course, be the 0.95 times 0.95 times 0.95, or 0.95 to the 20th. And that's going to give us 0.3585. So about 36%. Okay. And now for our last question. Okay, government data show that 8% of adults are full-time college students and that 30% of adults are age 55 or older. Because 0.08 times 0.30 is equal to 0.24, can we conclude that 2.4% of adults are college students 55 or older? And then why or why not? Okay, so I think this one's kind of obvious. No. They, being a college student and being 55 or older are definitely not independent events. So being a college student and being 55 or older, 55 or older are not independent. Okay. All right, so gather any questions. Let me know if you have any concerns about the at least one problem. We'll see a few in class. They don't come up all that often, but in any case, we'll get to practice some in class, and we'll see you then.